Today, we're jumping into a scientific paper that offers up a completely new way to think about one of the biggest goals in all of physics. And it's a theory that could, and I mean this literally, change, well, everything.
Just for a second, picture a world with zero wasted energy. Computers that don't get hot, power grids that are 100% efficient, levitating trains everywhere. That's the dream of superconductivity. But there's always been this one giant catch. You have to make things incredibly cold for it to work. But what if you didn't?
Okay, so where is all this coming from? Well, our source is a paper published back in 2022 in the journal Physica B. And in it, researchers from Thailand basically laid out a new theoretical playbook that just turns our whole understanding of superconductivity on its head. So the main claim here is, well, it's a big one. The paper puts forward a theory for making superconductors that are totally independent of temperature. I mean, think about that. No liquid nitrogen, no crazy refrigeration setups, just perfect, effortless conductivity, maybe even at room temperature. Now, to really get why this is such a huge deal, we need to take a quick look at the classic recipe. How does superconductivity normally work? For decades, the reigning champ of theories has been something called Ginzburg-Landau theory, and it describes superconductivity as a phase transition, kind of like water freezing into ice. As you cool a material down past a certain point, a critical temperature, pairs of electrons suddenly team up and condense into this single, unified quantum state, letting them flow with zero resistance. And this picture, the famous Mexican hat potential, is a great way to visualize it. Imagine a little ball sitting right on that central peak. At high temperatures, it's got a lot of energy, so it stays up there. But as you cool the system down, as you take energy away, the ball gets tired and rolls down into that circular brim. That brim, that's the stable, low-energy superconducting state. And the key thing to get here is that in the standard model, you have to remove heat. You have to get it cold to get into that brim. So how in the world do these researchers get around that need for cold? Well, they start by throwing a pretty wild new ingredient into that standard recipe, fractals. Now, when you hear fractals, you probably think of those cool, trippy geometric patterns that go on forever. But in physics, they're actually a super powerful tool for describing reality. See, real-world materials aren't these perfect, smooth, uniform things. They're messy, they're irregular, they're fragmented. And fractals, they give us the math to describe all that beautiful real-world complexity. And this, right here, is a total shift in perspective. The standard theory just simplifies reality. It pretends materials are perfectly uniform. The fractal approach says, nope, let's get real. Let's model these materials for what they actually are, uneven and complex. It's like going from an idealized blueprint to a model of the actual messy building. But okay, adding fractals, that was just part one. The next thing they did was even more fundamental. They basically tweaked the mathematical rules of the game itself. Now this part gets a little heady, but stick with me, because the core idea is actually pretty simple. In physics, there's this function called a Lagrangian. It basically sets the rules for how a system is going to behave. The researchers use something called a non-standard Lagrangian, which is basically like taking the official rulebook for physics and just asking a really profound what if. What if the fundamental math we use to describe energy worked just a little bit differently? All right, so let's recap. You take the standard theory of superconductivity, you add in the realistic messiness of fractals, and you run the whole thing through this new mathematical rulebook. What pops out on the other side? Something nobody saw coming. And here it is, the money shot, straight from the paper itself. The result of mixing these two ideas is a theory that predicts superconductivity with no refrigeration needed. And that's the crucial point. This isn't just a tiny improvement. It suggests a whole new type of physics is possible. Okay, but how? What's the secret sauce here? Well, the theory makes two pretty wild predictions. First, a property called coherence length, which is basically the distance over which these electron pairs act like a team, suddenly becomes independent of temperature. It doesn't fall apart when things get warm. And second, the effective mass of these electron pairs becomes quantized. That means it can only exist in specific separate chunks, kind of like the rungs on a ladder. And the physics that comes out of this new framework is, well, it's kind of weird. Just look at these plots from the paper. See how they're all lopsided? They're not symmetrical. That's a direct result of modeling the world with this uneven fractal geometry and this new math. The answers you get don't look like the clean, perfect solutions we're used to seeing in physics class. And as if that wasn't enough, here's another sign that this theory might be onto something big.
The paper notes that their new framework can also describe the switch between the two main types of superconductors we already know about, just by changing one of the numbers in their equations. This tells you the theory isn't just some weird, isolated idea. It might be a much bigger, more complete picture.
So this is all fascinating for physicists for sure. But let's pull back. What could this actually mean for you and me, for the real world? Honestly, the implications are just staggering. We're talking about power lines that transmit electricity with absolutely zero loss, which would save us billions and be amazing for the planet. We could build MRIs and maglev trains that don't need these massive, expensive cooling systems. This could unlock whole new types of computers. I mean, this is the holy grail physicists have been searching for more than 100 years.
So, what's the big takeaway here? Look, this is still a theory on paper. The real test will be building something in a lab that proves it. But it leaves us with this really incredible idea to think about, that maybe by embracing the messy, irregular, fractal nature of the real world, instead of always trying to simplify it, we might just find the keys to unlocking our biggest challenges.